Okay. So we will look into magnetic effect of current. So the important part, the first one is we need to look into Oersted discovery. Oersted discovery. Why Oersted discovery is important? Because say Oersted discovery was done in about around 1820, I think. Yes. So it was done in around 1820, Oersted discovery. Prior to this year, that means for the past 2000 years, people were thinking that a magnetic compass needle can be deflected by two things, either due to Earth magnetic field or due to magnetic stone's magnetic field,
Those
right?
magnetic dust-like particles, sir.
Magnetic dust, no, that ore, you know that ore we will get magnetite and hematite.
Yes,
These
sir.
are
Yes,
the
yes,
ore,
sir. Yes, sir.
magnetite and hematite, and then you just process it in the industry to make this kind of bar magnets or any kind of bar magnets.
Yes, sir.
This,
Yes, sir. I know.
right? So
Yes, sir.
prior to our Oersted discovery, everyone is thinking that a magnetic field can be created only by Earth or by some special stones like magnetite or hematite. And from this magnetite hematite, we used to make the magnets. Now, this compass, the compass which contains a needle, it will point towards North Pole. And so this magnetic compass is a very old instrument. It is 1,000 years old instrument, and this magnetic compass was this needle is deflected by the magnetic field only. So okay, there was no problem till 1820, but in 1820, Oersted made a discovery that magnetic needle can be deflected by current carrying wire also. That was the one of the starting point for electromagnetism. So this topic is always it is taught first because Oersted discovery said that your current carrying wire, simple one statement, that current carrying wire can deflect the magnetic compass needle. Magnetic compass needle. And how it does? Because this current carrying wire, CCW, current carrying wire produces magnetic field. Now you see this creates the relation between electricity and magnetism.
Sir, 1 second, sir. If I'm not mistaken, you mentioned, if I'm not mistaken, did you mention, you did, I think you mentioned before that this happens because the charges are in motion, no, sir?
Yes, correct.
Got it, sir.
Because current means that flow of charge only, and this flow of charge will produce magnetic field. That magnetic field, uh, but there is a problem here. We are talking about the year 1820, and electron was discovered in 1905. So after 100 years, electron proton was discovered. Before that, nobody were aware of these subatomic particles. So everyone was thinking that current is due to flow of charge. What is that charge? They don't know. Some
Got it.
positive charge, right? So that's why I'm not using that word electrons.
Yes, sir.
So a current carrying wire produces magnetic field, which in turn affects the magnetic needle. So there is a relationship between electricity and magnetism.
Yes, sir. Well, that was also because there's a stipulation that the only a magnetic field could change the deflection of the compass needle, no, sir.
Yes,
Is that?
yes, yes, yes. Because yes, a needle can be deflected only by magnetic field, not by gravitational, not by electrostatic field, only by magnetic field. Okay, it is really interesting that before 1900, scientists knew about electric field, about magnetic field, but they were not aware about the electrons, protons. That were discovered later.
That's only discovered like around late 1800s to early 1900s by Thomson, Rutherford,
Yes,
and all.
1900 and around 1905, Thomson, that
19.
Millikan oil drop experiment, Thomson
Yes, sir.
experiment.
That's when they discovered the properties, no, sir. The charge
Yes.
and how it's just the opposite of a proton, if I'm not mistaken.
Yes, it is just 100 years old theory.
Yes,
But
sir.
But current, electrostatics, all these are very, very 1,000 years old. So it's really interesting. So Oersted discovery was this,
Yes,
that
sir.
electric current produces magnetic field. Simple. But he did not give any formula. He just showed it logically that it is happening. That's it. The exact mathematical relationship between electricity and magnetism was given by two scientists combined, Biot and Savart. So now we have to look into Biot-Savart law, and here comes the complex maths, like dangerous maths is there in Biot-Savart law and other magnetic field concepts. Okay, and in your college you can expect, because this university, they want you to define everything in terms of complex maths. So let us look into this. So Biot-Savart law. Before going to this, you should know about the vectors. You should know about the vectors product, cross product, especially because here cross product will come. That is vector product, and how
Yes.
to find these, what do you call, resultant of vector product, direction of vector product,
So
everything.
that's the I cross J equals K. Isn't that pretty much
Yes,
what
yes, yes,
product is
yes,
in the sign convention?
yes.
And the inverse of
I
that would just result in a negative on the sign
yes.
convention of the product vector.
Yes. What we do, we take I j k in loop, and then
Yes.
if we have I cross j, that will give us k cap. If we have j cross k cap, it will give us I cap. K cross I cap will give us j cap. Anything other than that will give us minus sign. So j cross I will give us minus k cap.
Yes, sir.
So this we should aware of. And if we have two vectors A and B, and if we do the cross product, and let's say resultant is C vector, then C vector must lie in a plane where A and
Which
B
is
is there. So A and B need not be perpendicular, so we can write down anything. So let's say we have A and B vector, then C vector will be perpendicular to this.
so it lies in a plane that is perpendicular to the planes of both where A or and B lie in,
A
sir.
and A and
A
B line.
and B lie in.
B.
Got it.
These two vector must form a plane, and C will be perpendicular to that plane in, uh, you can say, as per right hand rule. What is right hand rule? Like, from, if it is A cross B, then you have to curl your four fingers along the direction from A to B.
To B,
In
and
that
that will,
process,
this is the thumb will give you the direction of C.
yes, yes. So
Got it.
we use RHS rule. So as per that, we will get the direction of C. Now, having said this, now we will look into the Biot-Savart law.
Yes, sir.
So uh, here there is one more term that will be used, that is called current element. Current element. So current element is a physical quantity which is defined by product of current and the small part of the wire, and it is a vector quantity whose direction will be along the direction of current. Now, let's say this is a wire where current I is flowing. This is the point where we want to find the magnetic field produced due to this current carrying wire. So what we will do is, let us take a small current element. So small current element means you take DL, and so you take DL, you draw one tangent line like this. This vector represents IDL, that is current element vector. Then you then you draw the position vector. So this is the position vector. Let it be R vector. This angle is theta. Now we have to find out the uh, magnetic field at this point due to this current carrying wire. Magnetic field is denoted by capital B. That is a standard notation. Magnetic field whose SI unit is Tesla. SI unit is Tesla. It is represented by B. So we want to find out B here. Since first we will look into the small magnetic field due to this small current element, which is given by mu naught by 4 pi. This is a constant value. Then the cross product of the current element and the position vector divided by magnitude of the position vector cube. This is the Biot-Savart law in its raw form. This is the basic format of Biot-Savart law. Now, depending upon how this wire goes, what is the configuration of wire, whether it is a straight line, whether it is a circular line, what kind of line it is, based on that, then you will have the actual magnetic field.
Got it.
Here, mu naught by 4 pi is 10 to the power minus 7. Mu naught is called absolute magnetic permeability in vacuum. It shows the number of magnetic field lines crossing a particular region. So about
Sir,
absolute
just a question, sir. Isn't that similar to the epsilon naught constant, sir? Because I thought that was also some sort of
yes,
permeability.
yes. 1 by 4 pi epsilon naught. Here epsilon naught is absolute electrical permittivity.
Yes,
This
sir.
is some sort of the same thing. So here we know that 1 by 4 pi epsilon naught is 10 to the power 9, but here it is 10 to the power minus 7. This is the raw formula. Now, what do you think? What will be direction of this magnetic field, small magnetic field?
Absolute direction of small magnetic field, it'll just be pretty much in the direction of DL cross R, no? So isn't that how its directions defined?
So based on this figure, can you tell me where it where it will lie?
It should point upwards, no, sir? Or
If you take ideal cross or no.
ideal cross R, then it will go downwards, no, sir? If I'm
Yes,
not mistaken,
yes,
because the
yes,
thumb will curl rightwards, then the fingers curl rightwards, so the thumb to point downwards.
yes. My
Yes,
my finger shows downward, so it is
yes, sir.
vertically downward. Okay, good, good. Now it means that here it will be now vertically downward. Actually, later on we will see that magnetic field lines are concentric circular lines. So here magnetic field lines are moving like this, going into the plane of the paper. So if magnetic field lines go into plane of paper, it is denoted by cross. And when it is coming out of the plane of the paper, it is dot. I think this is in CBSE also in class 12.
Yes, sir.
Cross and dot. Right. So here it will be cross. Okay. This is the whole idea about the Biot-Savart law. Okay. It can be written in another format also, which is much more useful than this direct one. Shall I erase this one?
Yes, sir.
So this can be written as mu naught by 4 pi IDL R sine theta by R cube and cap. So we have just put A cross B as AB sine theta. So R and 1R will cancel out. So it will become square. So IDL sine theta, it will become IDL sine theta by R square.
R square, sir.
Yeah, this is much more useful to us, where theta is the angle between
the current element and the position vector from the current element to the point at which you want to determine the magnet.
Yes. And that is the reason if theta is equal to 0 or 180 degree, which implies that point of observation is lying on the current on the wire itself. So point of observation lie on the wire itself. In that scenario, we know that sine 0 or sine 180 is 0. So in this situation, magnetic field is zero. So if we have any kind of wire and if you want to find out the magnetic field on the wire itself, it will be zero.
Got it, sir.
Now we will look into magnetic field due to a straight current carrying conductor. So let's look into that. So there are certain configuration. There are many configuration, but we will look into only the major ones, like magnetic field due to long straight wire. So if we have a long straight wire, okay, let us take just a straight wire first. Straight finite wire. Finite wire. So we will draw the line like this. So here current is I. Let us take this as point of observation and the perpendicular distance is, let's say, R. Now we want to calculate the magnetic field here. So what we have to do, technically speaking, we have to use the integration. We will take any random small this element and we will join it like this. We will find out the magnetic field due to this small current element and then we will integrate from this point to this point and given other parameters like what is the distance of this end point from this particular point. So this is quite deeper. We will not look into that right now. The formula that you will get is extremely important because that can be manipulated in many ways. For that, you join the top endpoint and the bottom endpoint. Then from the perpendicular direction, you take the clockwise rotation as alpha. So this is R, this is alpha. So clockwise rotation of the first endpoint, and this is anti-clockwise rotation, which you will take as beta. So magnetic field at this point will be given by mu naught by 4 pi. If you do the integration and plug in these values of alpha and beta, we will get mu naught by 4 pi I by R sine alpha plus sine beta and n cap. What is n cap? N cap is the
unit vector along the direction of the resultant magnetic field, sir.
So can you tell me what do you think? What will be direction of magnetic field here?
Sir, it depends on what the magnitude of alpha and beta is, no, sir. Because
No. So given this scenario, you can just see as a rough figure I cross R. Just do I cross R. So if you do I cross R, this is ideal
yes,
and
sir.
this is R vector. Okay.
Yes, sir.
Okay, it is vanishing pen. That's why. Okay. So this is ideal and this is R vector. Can you do I cross R? It is going, your thumb is, when you curl your fingers of right hand from ideal vector to R vector, then your thumb is going into the plane of the, into the plane of the paper. You see?
Yes, sir.
That means magnetic field here is cross.
But I have a doubt, sir. But won't the magnetic field as a whole be determined as a result due to the angle inclination to the upward part of the finite wire and to the downward part, sir? Especially given that you don't know where the point is, sir.
No, whatever it is interesting to note that whatever alpha beta, if it is the direction of current which basically defines it. Why? You see, because Your alpha may be this, whatever. Maximum it can go up to this. In that case also, you see it will be cross only because we have to do I cross R. Now understand this thing. This is I and this is R, right? Where in this situation also, because the I cross R is a normal vector, so it will lie perpendicular to the plane. It does not matter where it is. Understand this thing.
Yes, sir.
So
So the R vector is still gonna be static no matter what, where, how long the alpha stretches. Is that what you're trying to
yes,
say?
yes. You see, you just define one plane like this. Now this is I. If our R, so I means ideal. So this is R vector. Fine. Okay.
Yes, sir.
In that situation also, if you look into the magnetic field, it will go here.
Yes, sir.
Instead of this, if you take R vector this, then also
It's
it will
still
be
gonna go
here.
downwards, sir.
You see this. Now it will change if you go to that place. If you go to that place, then ideal cross R will, if, you have to curl your fingers from ideal cross R to R. Then your magnetic field will become
It'll
this.
go
That
upwards.
means till 180 degree wherever you put, magnetic field will be downward, and for that side, wherever you put your point of observation, that will be upward. Am I clear now?
Yes, sir. You're
So
clear.
so that's why we did it like that, that for any current carrying wire, magnetic field on this side will always be cross. Always be cross. This can be also done by using right hand thumb rule. There is a yeah, this is in CBSE also, right hand thumb rule. It says that you imagine that you are holding the wire with your right hand. You are holding the wire with your right hand such that thumb represents the direction of current. Then you curl your fingers. This curling of fingers will give you the magnetic field lines. Now you see, all the right hand region you will get only cross, and all the left hand region you will get only dot. That is, magnetic field is coming out of the plane of the paper here. Am I clear?
Yes, sir.
So, fine. And what is the formula? So formula is B is equal to mu naught by 4 pi I by R
Sir, one
sine.
second, sir. I have a doubt, sir.
Mhm.
You mentioned that the curling of the fingers along which direction it curls represents whether the magnetic field is either into or out of the plane of the paper, sir.
Yes, yes.
So, but what would determine which direction we would even need to curl our fingers in? So, say that the fingers direction do determine. So, but how would we know which direction to even curl our fingers? And given that we are pointing our thumb upwards, sir.
Okay. Tell me one thing. You take your fingers like this, right?
Yes, sir.
Okay. So this is the imaginary wire, and you are going to hold it.
Yes, sir.
You are going to hold it, right? Can you tell me in which direction you can curl your fingers?
Oh, you can only curl it
Yes,
rightwards
yes. We can curl only along this direction. We
direction. So
can,
the magnetic field is inevitably bound to be
yes, cross and dot here. You see, we cannot curl it in opposite direction. If your current is going like this, then you have to change your entire hand posture, because you have to
you
point.
have to
So
you have to keep the thumb upwards, but to curl it in the other direction, sir.
yes, you see this one. Now it will become like this.
Got it, sir.
Hmm. Then it means that magnetic field lines will go like this. This is cross and this is dot. Is it okay now? Clear?
Got it, sir.
There is unique direction possible. That is the best part. See, but with there may be a person who have special capability to curl in both direction. So obviously we will not consider that one. It is the general one. So sine alpha plus sine beta, this is important. Alpha and beta you have to find out by looking into the configuration. And magnetic field is a vector quantity. So if we have more than two wires, find the magnetic field due to each wire and then do the vector addition. Is it okay?
Yes, sir.
So can you try this? Just no need to do the final one. So that's why we will just take the symbolic data. So it is a square circular, this is a square current carrying coil of length L. Current is I. What is the magnetic field at the center? What will be the magnetic field at the center?
Sir, the magnetic field at the center, I'll just calculate it numerically, sir, but it will just
Mhm.
be, I think, 4 times of nu naught by 4 pi times I by L times of root 2, sir, because the angle covered from the point to the ends of the sides will pretty much be 45, because the diagonal length of a square is pretty much the same now, sir.
Yes, it
I'll
is correct.
calculate the exact answer, sir, but I think I got the explanation. I think you understood my
Yes, 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 yes. I think it is correct. So we will take just one wire. Due to symmetry, we will first find out the magnetic field due to just one wire,
one
which
wire, sir.
so it is 45 degree, it is 45 degree, and this is L by 2. So B is equal to mu naught by 4 pi I by L by 2 sine 45 degree plus sine 45 degree, that is root 2 by 2 plus root 2 by 2, that is root 2. So if you just simplify mu naught I by L, this one will be 2 will go there, 2 root 2 by 4 pi. This is the magnetic field due to just one wire.
Yes,
Now
sir.
the direction is cross. For this also direction is cross. For this also direction is cross. For this also direction is cross. So since we have cross due to all of them, and all of them are symmetrically placed, so that means our net magnetic field will be 4 times of magnetic field due to just one wire, and this is equal to we can just write down mu naught I 2 root 2 by pi L. This is the answer, and the direction is cross. This is our final answer.
Yes, sir.
Okay, good.
So I do have a doubt, sir. This is regarding
Mhm,
an example in a previous chapter, sir. When
mhm,
we did this kind of square arrangement with, like, say, 4 charges at the corners,
mhm.
did we need to would we need to consider even the electric field at, say, the center point? So would we need to consider the electric field due to diagonally opposite charges, sir? Like, I'm just kind of confused now that this example has come up. Like,
Diagonally.
same arrangement, but
Uh-huh.
say charge of magnitude plus q is placed at all 4 corners of the square, and then calculate the net electric field at the center of this square. Would we need to consider electric fields only due to the sides, only due to the charges along the sides of the square, or even along the diagonals? Or now that this example's come up, I'm a bit
Okay,
confused.
okay, okay. So, as per my understanding, what you want to say is that we have, let's say, plus Q charges
Q plus
here,
q plus q and plus q,
plus
sir.
Q and plus Q, and we want to find out the electric field at this point, right?
Yes, sir. Would we need to even consider the plus q along the diagonal, sir? Like, I was just confused whether we need.
Diagonal. So we,
Before we consider the electric field due to the charges along the sides of the square, sir. But
okay, so we have plus also here, right?
yes, sir.
Okay, 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 okay. So that means you are saying that we have charges distributed here also, and apart from that, we have four charges at the corner also. Is it what you
Yes,
want to
sir.
say?
Yes, sir.
Okay. So in that case, interestingly, due to, yes, we have to find out electric field due to everything. Due to these two, it will be nullified.
Yes, sir.
Due to this two, it will be nullified. Due to this two, it will be nullified. Due to this two, it will be nullified. Zero. Electric field will be zero.
So I have a doubt on how you can say that the charges due to the configuration of the two opposite sides being nullified. So is it just because both of them will be along the
Because
same direction, but since they are in the opposite direct sides?
because okay, because it is the same distance, let's say x. So here my electric field will be directed along this. For plus q, here also electric field will be directed along this same magnitude but opposite direction. So they will
Yes.
cancel out each other. Because we know E is equal to KQ by X square. So you
Yes.
see Q is same, X is same. So
Yes.
magnitude is same. Since it is plus Q, so this electric field is due to this one. And this one is due to this. They are equal and opposite, so they will cancel out each other. Is it
Got it.
okay? Yes. Okay. Now, this one. Okay, good. Fine. Now let us look into the magnetic field.
Yes, sir.
Magnetic field due to long straight wire. So long straight wire. So let us draw this one. Okay. So current I is flowing. It is a long straight wire. That means what happened that long means if this is the point of observation at which is at a distance of x. Now you see long means you just think about this one was our alpha. If you increase the length, alpha will increase. Alpha will
Yes.
increase. Alpha will increase. It
Yes,
will
sir.
increase. Maximum it can go up to 90 degree. When this part will become infinity, alpha will become 90 degree. So alpha is equal to 90 degree.
Got it.
Similarly, this part when it will go up, beta will be also 90
So
degree.
90
For
degree because there's no exact angle of inclination for it to
yeah,
go.
because it is becoming parallel, no?
Yes, sir. Yes, sir.
So it means that magnetic field at this point will be given by mu naught by 4 pi I by
Times
x 2 sine
yes.
90 plus sine 90 1 2.
1
So
plus
it
1.
is mu naught I by 2 pi x. This is one of the most frequently used formula that you will encounter henceforth. So magnetic field due to long wire is given by mu naught I by 2 pi x. This one. Is it okay? So a
Got
long
it.
means both side means your point of observation is anywhere in between, and this side it is also infinity, this side also infinity. Okay. And direction will be same thing. It will be cross, it will be dot. Okay. Now tell me this answer. Have you understood this part?
Got it. Yes, sir. I did.
Okay. Okay. So tell me this answer. There is a long wire. Okay, there is a long wire, but the problem is this is going to infinity. Current I is there, but our point of observation is lying at one end of this infinite wire. It was infinite, but we located its end point and we are here. It is x.
So it's only infinitely long about one end of the wire, sir.
Yes. So what will be magnetic field
So
at this
wait, sir.
point?
So are you trying to calculate the magnetic field at a distance x from the endpoint of one of.
Yes. So basically, we want to find out the magnetic field due to semi-infinite wire.
So in that case, wouldn't it just be mu naught I by 4 pi x, or given that it's only infinitely long about one end, but since it's only a distance x about the other end point, that
Hmm.
angle of beta would pretty much come out to zero, no, sir?
Yes, yes,
It was
100%
only
correct.
mu naught I by 4 pi x times of 1
Hmm.
plus 0.
So alpha is equal to 90 degree, beta is equal to 0 degree. That's it. Good. So our magnetic field will become mu naught by 4 pi I by x. That's it. This is the answer. And
Yes.
cross sign. Okay. What if the same point of observation we take at some distance here such that this angle is making 60 degree? Can you find out now? So this is making 60 degree and this is x. Find out the magnetic field at this point.
Sir, in that case, I think it would be mu naught I by 4 pi x times of half plus 0, no, sir?
What is alpha and beta? You just tell me alpha and beta. That is enough.
Alpha's 30, beta's 9, beta is 90. That's how I
Don't
see
get
it.
confused about alpha and beta. Alpha is that angle. Alpha is the angle made by, you see, what is alpha? You join this. You join this. Alpha is this.
Okay, that alpha will be 90, sir. That
Yes.
alpha
And
will be
beta?
90. Beta, I
Beta?
think, is 30, sir.
Yes, right. It is 30.
Because the angle of theta is from the point to the leg and not the angle of inclination between the point and the perpendicular to the point about a line passing through the endpoint. So
Yes, correct. Good. So that's right.
so it will then
And
be half plus one in
hmm,
the bracket terms. So mu naught I by 4 pi x times 3 by 2, sir.
yes, good. And then we have this one also. Okay, just a minute. Yes, we can find out, no problem. That's okay. Now let's move to magnetic field due to circular current carrying coil. Magnetic field, these are the important ones we are looking into. Magnetic field due to circular loop, circular current carrying loop. So uh, let us take this as circular coil having n number of turns. Radius is r, current is I. Now, how magnetic field lines will look like? Magnetic field lines are very, very complicated. So, okay, so current we have to flow in this direction. So, yes, it will go like this. It is too much complicated, but we don't take that complications. So this is the magnetic field lines pattern. And around each there will be magnetic field lines. So it is too much complicated because at every point magnetic field lines will still like this. So at every point magnetic field will be like this, and due to whole one we have magnetic field lines like this. But we will consider the magnetic field lines which is passing through the center along the axial line. We will take this as magnetic field lines. Is it okay?
Yes, sir.
So we will not take all these complexities, even though it is complex. We will take magnetic field lines only at the only along the axial line. And how to find this magnetic field lines? Here, do opposite thing. Use the right hand thumb rule, but curl your fingers along the direction of current, and thumb will represent the magnetic field.
Yes, sir.
Right? Okay. And how to find the value? So here we will take a point at a distance of x and take a current element here. Due to this, find out the magnetic field. This magnetic field is now this is actually very tough one to prove it, but we will do it when your class will start. Then we will see. If your professor tells you that whether if you proves it, then only you do, otherwise you can leave it. So it's like this, that if this is the current element, if this is the current element, this is the position vector, then our magnetic field will be perpendicular to this plane. You have to imagine that what we are doing. So this is the dB, ideal cross R. This dB is perpendicular to the plane which contains ideal and R. So it's like this, that this is the plane. It is the plane, and this dB is perpendicular to this plane. Can you visualize this?
Yes, sir, I can.
So, and then we will take the integration, and after doing all these sort of things, we will get magnetic field lines at this point along this only, and this magnetic field is given by mu naught by 4 pi I 2I pi r square into n by r square plus x square 3 by 2. This we will get. Actually, this denominator is because of this value z. You know, in the denominator we will get actually z cube. And as per Pythagoras theorem, z is equal to r square plus x square root. Now, if you do z cube, you will get this one. So, if you have any confusion, you can just remember that it is nothing but z cube. So, z cube is r square plus x square 3 by 2. So, this is what it is in the denominator. Okay. And instead of pi r square is nothing but area of the coil. Right. So, that means we can write magnetic field along the axial line is mu naught by 4 pi to NIA by Z cube. This we can remember. Is it okay?
Yes, sir.
Right. Now, just by looking into this formula, can you tell me if this X becomes 0, what will be magnetic field? That means magnetic field due to circular loop at the center. What will be this value?
Won't it just become, technically it feels like it will become infinite, no, sir? Because
No, why? You're just here. X is the variable, but it is only here.
Oh,
So,
wait, sir. Okay, wait, sir. I think I made a mistake. But in that case, it would just be due to r cube, sir. So it would just be mu naught by 4 pi times 2 ni pi by r, no, sir. Because r square term will then get divided by an r cube term where the x will then become 0 because it's not at a distance along the magnetic field line along the center, son. So the x square term will become 0. So it'll just be inversely proportional to r, son.
this one will be the answer. And it is again one of the most frequently used formula.
Not ni by 2r, son. Yes, sir.
Mu naught Ni by 2R. For a single loop, it is mu naught I by 2R. So where the student get confused, because of long wire, formula is mu naught I by 2 pi R. Due
Yes,
to circular coil of single turn, mu naught I by 2R. So difference is only pi, remember. For straight wire, you will use pi term. For circular wire, you will not use the pi term. Understood, no?
Yes, sir.
So this is what it is, and yes, okay. Then if we take just a part of it, okay. Now this circular coil we will represent like this. Mm, shall I erase this one?
Yes, sir.
So if now if we take just circular arc, that means this is the okay. Let me make it a little smaller. So let's say we are talking about only this part. So this is the part of a circle. If you complete this circle, it will make like this, but our wire is only this much. So you find out the center, find out the angle which is subtended by this particular arc. Let's say this is I, this is R. Then magnetic field at this point is given by mu naught by 4 pi I by R into theta. This is again a commonly used formula. It is magnetic field due to a circular arc, not due to a circle, due to circular arc. If you complete the circle, your theta will become simply 2 pi. So in that case, magnetic field will become mu naught I by 2R. That we already know that this is the formula.
Yes, sir.
Is it clear?
Yes,
And
sir.
here
But the
magnetic
n
field.
variable, if I'm not mistaken, sir, only comes due to the number of turns being made in creating that loop. No, so if it's just like a single circular wire made due to one single full loop, then the n parameter just becomes one. No, so just to be clear.
Yes, yes. In all these formulas, we are taking n is equal to 1 only. N can be other values. Depending upon that, you will get these answers.
Got it, sir.
Okay. So these are some of the important formulas that are necessary. Whether I have sent you any document related to this?
Related to this, I think you did, sir, but I wasn't able to load it on my laptop, so I only just went through it yesterday, so.
Okay, okay, okay. So I'm
Like
sending
I'm
you
almost
again.
halfway done going through the document you sent that contains this, sir.
Yes, okay, yes, I have already sent it. Right, right. So no need to send it again. You can just download it. You'll get it. Good.
Yes, sir.
Uh, okay, that's fine. So what we will do is, okay, then we will meet tomorrow. Tomorrow 9:30. You can confirm, right?
Yes, sir. So what I'm thinking is my structure, ideal timing is from 9:30 to 10. We'll, if possible, we'll try finishing this through fully, sir. We'll just finish the magnetic effects fully, and then from 10 till 11
Go to
we'll
discrete
focus
maths.
on number
If you
theories.
if you look into the PDF file that I have sent you, it will be really helpful because we will just go through that and like okay, these are the formulas. This is the special thing that you need to note. So in that case, we can finish it up.
Yes, sir.
Please download that or at least take a printout of it.
Yes, sir. I've just now managed to download it during when in class. So
Okay, okay. Because that's what we are going to discuss. So if you look into this, only few things we will discuss, and that will be okay.
yes, sir.
Okay, then tomorrow we'll meet again. Hmm?
Yes, sir. We will, sir.
Okay, then. Bye bye.
Yes, sir. Thank you, sir.
Thank you.